In this video we will briefly discuss how to create chemical bonds out of electron waves. Okay, and the theory we are going to discuss in this chapter 1.7 is called valence bond theory. So it focuses only on the valence electrons. So now, basically a bond occurs when atomic orbitals overlap. Can you remember from chapter 1.6 where we discussed that atomic orbitals essentially just are waves? And so overlapping atomic orbitals is the same as just overlapping waves. And so we can look at some simple examples here. We'll have these 2 points, and each point represents an atom, and so we'll have 2 waves, right? Let's say they are both positive, so they're both blue, and there's a wave around each atom. But the distance between the 2 points now represents the internuclear distance, so the distance between the 2 nuclei of these 2 atoms. Now, if both waves are positive, then they reinforce each other. So what we overlap the 2 waves, is we get a bigger wave, and the whole wave is positive still, and we're getting so-called constructive interference between the 2 waves. So that means that's the same as getting a bond, because you see the amount of electron density now in between the 2 atoms is actually higher, and so that this additional electron density kind of acts like glue to pull these 2 atoms together. Okay, that's how a bond forms. But now, of course, we can do something similar, where we have one atom with a positive wave on it, and a positive wave function on it, and the other atom with a negative wave function. So if we overlap these 2 waves, now the 2 waves partially cancel each other out in the middle. And so this also happens generally between when we have a valence bond theory occurring, right? So now, after we overlap those 2 waves, we get a positive part, and in the middle the wave function is 0 because everything cancels it. The 2 wave functions cancel each other out completely. Then on the right we're getting a negative portion of this orbital. Right? So here we have so-called, first of all, we have a node in the middle, and we have so-called destructive interference. Again, both of these situations now occur in valence bond theory. But only constructive interference actually results in a bond. Destructive interference generally results in a so-called anti-bond, and so that kind of pushes the atoms apart, as we will see. Now let's see what happens in 3 dimensions. For example, for the bond in H2. So the bond in an H2 molecule simply results from constructive interference. And what are the 2 orbitals involved? The 2 1s orbitals. Right? So here's the first 1s orbital, and of the first atom, the first hydrogen atom, and then we put that together with a second 1s orbital of the second hydrogen atom. Put them together, and you see we get constructive interference in the middle, and that gives us the bond between the 2 hydrogen atoms. Now, in this case, you see we get direct overlap between those 2 1s orbitals, and this can also happen with p orbitals. But in either case, you get a kind of head-on overlap between these orbitals, and then you get a bond which looks kind of like a sphere if you look at it along its axis, right? Projected along its axis. And so in this case, because it looks like a sphere, it is spherically symmetrical, it's actually called a sigma bond. Okay? So now in this case, because both 1s orbitals are now overlapped in a constructive interference fashion, the electrons actually spend most of their time now in the middle between the two nuclei, and that's why we formed a bond. And so this overall orbital space where the electrons are in now, it's delocalized over the whole molecule. It's called a molecular orbital. Now there are different models, and basically what we've talked about already, it's kind of like an evolution where you can have a simpler model and that kind of explains things but not so well, and there's a more fancy model, and then there's an even better model, and yeah, so I want to just briefly put this in perspective of the models we have already discussed. So we have seen Lewis structures, which is really the simplest kind of model, but many things Lewis structure cannot be explained simply by Lewis structures, as you'll see. Then we have now very briefly touched upon valence bond theory, where we only look at the valence electrons, and it's already a much better model than Lewis structures, but still not the most powerful. The most powerful model is called molecular orbital theory, and we will very briefly touch upon it in the next chapter, in chapter 1.8. And yeah, so thanks for watching this video. I look forward to telling you about molecular orbital theory next.